A heartfelt welcome. Today we will calculate the center of gravity and the main central moments of inertia for a figure that does not have a symmetry axis, which means at the very start we will define some initial axes. These will be our arbitrary axes. Let's say we position them here. This will be our y-axis, or y0, but let's just call it y. Here will be our z-axis. Next, we are able to divide this shape into simple figures. Let's say we divide it in the following way. This will be our first figure, a quarter circle, the second figure, a triangle, and the third figure is this entire rectangle from here to there. Okay, now let's start by calculating the centers of gravity. That means listing in order the centers of gravity in our system. So now, when we will denote the centers of gravity y1, y2, y3, we always start from this point. Which means now we go from y1 from here to somewhere there. y2 also from here, also from our z-axis, we move on the y-axis. This is our y2. And then we move on our y3 axis. Here we are able to also find this center. Of course, the center C3 is here. The center C2 is here. We'll discuss exactly where it is in a moment. And C1 is here. Why is that? We will discuss it. Because although we might remember from high school, usually a lot of people have a problem with this. It is there in our tables. We have snippets from tables here in the top right corner. So what do we see here? That for the figure y1, we are not completely able to specify directly, because we sort of have this remainder here. So just as here it's 4r over 3 pi, here effectively is our radius r, we have this. And we know that from here to there it will be 4r over 3 pi, which is 4 times. We already substitute this 3 with r. So 4 times 3 over 3 pi. But since we are interested in this distance y1, we will write it as 3 minus 4 times 3 over 3 pi. We quickly punch this into the calculator. We get 1.727. Notice that this is all dimensionless. Probably in practice it would be in centimeters or some other unit. Now we will do it without units here for simplicity. Then we have y2. And now y2. Again, we don't have directly in the tables, because we have such information about the triangle, after all, from high school too, that from here to there we have 1/3, and thinking simply from here to there we would have 2/3 of this dimension. And here we have exactly this situation. We record 2/3 out of 3. So this is our 2/3 out of 3. 2/3 out of these 3. We write it down, we have a 2. y3 is the simplest because we are in the center of gravity of a rectangle with dimensions 3x6, but we are interested in this distance. So on one side here we have already 3, and we know from the dimension line that here we have 3. And we add this piece here. So we have 3 plus 3 halves, because half of 3. You don't even need a calculator for that, it comes out to 4.5. Next, we write down the centers of gravity on the z-axis. We can immediately see that for the z1 axis we will have such a situation. This is our z1, right? Then for z2 we have this. We go kind of under the axis. Notice, it will actually be taken into account that it will go opposite our z-axis. And here we have the center of gravity exactly on the axis. Therefore, we immediately write z3 as 0. And now for z1, we take the value from the tables. That is 4r over 3 pi. So we have 4 times 3 over 3 pi. Well, it is the same, right, as last time. 4r over 3 pi. Alternatively, we can write it approximately, but we'll do that in a moment. However, on z2, we simply have 1/3 of 3. But importantly, as I said, we are below the axis. So we write minus 1/3 of 3, which is minus 1. Here we have approximately 1.273. Calculated on a small calculator. All right, so now, the next thing we need to calculate the position of the center of gravity for the whole figure. are the areas of individual simple figures. So we write a 1. We remember the area of the circle. It is nothing other than pi r squared, which is pi times 3 squared. Divided by 4, we get 1/4. 7.07. Then we have the area of the little 2. It's a triangle. The area of a triangle is 1/2 times b times h, we remember. 1 over 2 times 3 times. 3 is 4.5. But this could be done without a calculator. Then we have a 3. And that's the simplest because it's a rectangle with dimensions 3x6. That gives us 18. Now we plug this into the formulas. I will present the formula in the simplest possible form. y1 a 1 plus y2 a 2 plus y3 a 3 divided by a 1 plus a 2 plus a 3. Now then, what we wrote at the top, that is y1 times a 1, y2 times a 2. This is nothing more than static moments concerning the z-axis. This is an additional piece of information, let's say, but so that you are not surprised that it is sometimes written this way. Now I'll quickly input it into the calculator. So I will get 3.457. I still do not know the center of gravity's location. I only know one of the dimensions. Why? Because now I can preliminarily draw it. 3.457 will be somewhere here. 3.457 comma, meaning somewhere on this line, is the center of gravity. We don't know exactly where yet, so we search for ZC. Of course, the formula is identical. Only on the top we have static moments concerning the y-axis, meaning Z1A1, Z2A2 plus Z3A3. Again divided by the sum of the areas. When we input this into the calculator quickly, we get 0.15. We will also mark this 0.15, meaning we are somewhere there, slightly above. This is the center of gravity for the entire figure. Here we have some axis. Let's call it for now, or maybe YC. Zetka. Let's underline what we have now. These are not yet the main central axes. These are only the central axes. Not yet the main ones. We will move on to the main ones shortly. For now, we have the position of the central axis. Now, to calculate the moments of inertia concerning these central axes, we will calculate the moments of inertia of individual simple figures, concerning their centers of gravity. So in reality, we will have some I underscore y2, I underscore y1, I underscore y3, I underscore z1, I underscore z2, I underscore z3. Then we will use Steiner's theorem to bring everything to one place. And now then, what is not needed? All these calculations we just performed, at this moment, are not needed. So I will now delete them thoroughly. However, the positions of the centers of gravity of individual figures will be needed for Steiner's theorem. Let's start writing them down now. We have the position y1, z1. Now we will also have the moments of inertia I underscore y1 and I underscore z1. And for y1, because we have a quadrant, we look up in the tables, what's going on here? We have such a formula, 0.0549 times r to the power of 4. Of course we can derive this. However, let's assume that we have this data. So 0.55, let's not be too precise, times 3 to the power of 4 equals. Quickly input into a calculator, 4.447. Again, y2 also according to the formula. This is a standard formula for a triangle. That is, we have nothing but bh to 3 divided by 36. This is also, of course, here in the tables. And here in this case, b equals h. So let's write down 3 to the power of 4 divided by 36. On the calculator, it's 2.25. Then we have y3. For a rectangle, let's take a look at the table. For a rectangle, we have bh to 3 divided by 12. Notice that there are different axis names here. But we don't look at it like because we have the y-axis, we'll take yc. That would be silly. We look at whether the axis is horizontal or vertical. We are now examining horizontal moments of inertia. For us, the y is a horizontal axis. So we take I_xc. Put a 3 divided by 12. It's BH, obviously. For this rectangle, b is 3 and h is 6. So we have 3 times 6 to the power of 3 divided by 12. Calculator at hand. Elegantly, it comes out to 54. And now let's write down the moments of inertia on z. I_z1 equals. So I_z1 equals the same. Notice that this formula should be clearly written here. That x equals yc, however, it is exactly the same for both axes. Here again, it's the same. Our vertical axis is z, in the tables it is y. However, we do not look at the symbols. We would have concluded that we don't have such a formula in the tables. We just look at the fact that this is a vertical axis. Now we have it like this. 0.055 times 3 to the power of 4. That equals 4.447. And now z2. Again, it is the same, because formally here we have not bh to the power of 3, but hb to the power of 3 divided by 36. So pay attention. A different dimension is to the power of 3. However, here we have exactly the same formula, because b is equal to h, so it also comes out to be 2.25. Next we have I_z3, and I_z3 is equal to, we look at the tables, but you can probably guess. That something will change here. It will change which term is raised to the power of 3, because bh to the power of 3 divided by 12 is b to the power of 3 times h divided by 12. If we now take a look, we have a reversal of this situation. As it was 3 times 6 to the power of 3, it is 3 to the power of 3 times 6 divided by 12. So this equals 13.5. Indeed. Now then, I have the individual moments of inertia of the component figures. And now I have to transfer them to the center of mass to get the central moment of inertia of the entire figure. We do this using Steiner's theorem, which generally looks like this. Ic equals Ei1 plus a 1 in brackets z1 minus zc squared. Now then, this term z1 minus zc is nothing else but the distance. Pay attention between y1 and yc. I think I'm running out of available colors here. We'll try green. It is the distance between the y1 axis and the yc axis. So this is exactly the distance here. Right? Between this axis and that one. This is that little element. And now for us it is simply z1 minus zc. We have calculated z1 minus zc. It doesn't make sense in this particular problem. To look for it in the diagram, we can derive it directly from the formulas we used. Of course, for the individual terms, it will be similar. I will now immediately enter this into the calculator. I highly recommend recalculating it yourself. The truth is that very often the errors in these tasks do not stem from someone not knowing the theory, but simply from entering values incorrectly into the calculator. When entering it into the calculator, it comes out as 75.97, and that is already the central value. Not the main one yet, central. We have the next Isc, which equals is1 plus a 1. In parentheses, y1 minus yc squared. Notice this is exactly the same. We used to shift the y moments with respect to the z-axis. Now the z moments are shifted to y. So we shift z1 to this position of zc, which means we now have such a distance. Of course, for individual terms, it's the same. Plus is 2 plus a 2y2 minus yc squared plus is 3 plus a 3. In parentheses, y3 minus yc squared. It equals. We put this into the calculator, and on the calculator, it elegantly comes out to be 70.49. Now then, if we were asked about the central axis, then the topic is closed. Usually in such tasks, we are not asked about the central axes. They ask us about the central main axis. And for the central main axis, we are still missing a transformation of what we got in the central into such axes where the deviation is equal to 0. So we need to calculate the deviation moment. The deviation moment is most often in these tables for simple figures, marked as I_xy. I will denote it as d. Now we know that it's exactly the same, and I need to list it for individual figures. And in such an arrangement, let's make a bit of space here directly at the figures. From these y1, y2, etc., I will unfortunately continue to use, but I assume we have it available somewhere. d1 equals, d2 equals, d3 equals. Now I look at the table. Deviation of the rectangle 0. Wonderful, I write 0. Now then. As for the deviation of the other two figures, it's unfortunately much more interesting. Why? Because the deviation of the one must be recorded with a specific sign. In the tables there was a minus. -0, so 0,165. And I will write 0,0165 times 3 to the 4th power. I'll write immediately. In a moment, we will enter the approximate value. Let's quickly use the calculator. 165 times 3 to the power of 4. So we got 13365. And now I'm looking, I wrote down a plus, because we have a rule that if this quarter circle is drawn this way, then we have a plus here. Note that when we have such a triangle, our 2, this is the position. And it will indeed have a negative deviation. So -3 to the 4th, because here is b squared, h squared. b equals h for this figure indeed. So we have 72, minus 1,125. The topic of deviation is closed for individual figures. I will not draw it in the diagram. Now we have to calculate the deviation for the center of gravity. We had it for individual figures. Now we accumulate it. We have d1 plus, you won't believe it, accumulation from 2. It's like transmitting the deviation along both axes, right? Both on the z-axis and on the y-axis. Plus d2 plus a 2. You can already see the mechanism. z2 minus zc. y by 2 minus yc. Plus a 3. Sorry, plus d3, of course. And now plus a 3. z3 minus zc. y3 minus yc. It equals, we put it into the calculator. We get minus 8.8. Now we have a technical note, listen. Because moments of inertia are always positive. Even if the sky falls down, moments of inertia, both individual figures and central moments of inertia, are positive. Deviation, not necessarily. A moment of deviation can be positive or negative. Here it actually came out negative, and that's what it was supposed to be. Now, what remains to be calculated are practically only the central principal moments of inertia. So let's calculate it all the way. There are just 2 formulas. Calculating, that makes 4. Because now we have such a situation. If we want to calculate the central principal moments of inertia, it's a moment rotated by such an angle. For the deviation to become 0. There's a ready formula for this. We will not, of course, demonstrate the derivation of this formula, because you can find that somewhere in textbooks. I'm now writing down the first main central moment of inertia. We'll calculate the second one in a moment. It will only differ in sign, so it will be almost the same. However, these will be the largest and smallest moments of inertia. This one is the largest because there is a plus sign here. Meanwhile, the second will be the minimal smallest main central moment of inertia. The minimal smallest. We substitute into such a formula. Of course, the deviation regarding the center of gravity. And we calculate it on the calculator. We get the respective results. 82.45 and 64.01 centimeters to the power of... Sorry, without units. If they were in centimeters, they would be centimeters to the 4th power. But here we have dimensionless, so we leave it in this form. We already have the main central moments of inertia, but to draw them, I need to know how they are rotated with respect to the central axes. Of course, we could choose freely. But let's agree to calculate the tangent of the maximum phi. And it equals d over Isc minus I1. We substitute it. We get 0.736. Of course, this is the tangent value of that angle. So when we convert it to an angle, we have that φmax equals arcus tangent of this value. We get approximately 36.36 degrees. Similarly, we could optionally choose the tangent of the minimal phi. But since we know that the central axes are at an angle of 90 degrees to each other, similarly, the main central axes must be at an angle of 90 degrees to each other. That's 1.36 in the negative. And similarly, from this, the minimal phi equals minus 53.64 degrees. Now we want to plot this on the drawing, so we go back to our drawing, which is a bit dense now. But we'll try to manage somehow. And now, from the horizontal axis at point C, whose position we know, calculated earlier, we set out the direction I1. And that's our angle 36.36 degrees. And similarly to it, here we have I2. And first of all, I2 is at an angle of 53.64. So we know that we need to rotate by that much. Of course, this is drawn by eye. In practice, you will do it correctly. And secondly, we know it must be at a 90-degree angle. And these angles indeed sum to 90 in absolute value. Why did I1 go in that direction? Because with the adopted y-axis and z-total axis system, we know that a positive angle is left-handed, therefore 36.36 in that direction. However, phi was negative, 53.64. Therefore, it went right-handed clockwise. This is the end of this task. Thank you very much for listening. Remember to subscribe to our channel, and if you have any questions, the comments section is for you, don't hesitate. On our website, you will find more tasks from this section, with full step-by-step solutions, and as usual, we kindly recommend ourselves. Until next time.